course, I want to see the participants. So I want to see the chat window. All right, so this seminar is about ATENA software and how I would like to devote it to the capabilities, some examples for performing dynamic analysis in ATENA, with the emphasis to seismic modeling. Let me first, for those of you who may not be fully familiar with ATENA and what about our company, so let me just say a few words as an introduction. So ATENA and also our company, we are devoted to developing technologies for advanced modeling of reinforced concrete structures. This slide summarizes the range of problems we are typically dealing with, starting from bridges, buildings, of course, nuclear containments. Nowadays, we are very much involved also with these offshore structures for wind, for electric power generation from wind. These structures are typically steel, but in this case, they often have a grouting, concrete grouting, connecting the top part of the structure with the bottom part, which is embedded into the seabed. Our company, Czerwenka Consulting, we are a small company, about 20 people, but we are very much internationally active all over the world. And we are located in Prague. This is the picture of the Prague. This is a picture of the Prague in the fall. Now, of course, we are starting to have a nice spring here. Finally, also the spring weather is coming. This shows our activities all over the world. These yellow marks indicate the countries where we have a representative. And as I told you, we are developing models and technologies for modeling of concrete, but not only concrete. The models can be used for other brittle materials. We also have models also for steel, soil, and so on. But our main emphasis is, of course, on modeling brittle materials such as concrete, including, of course, the reinforcement. And this summarizes very briefly the main features of our material model. So it uses this Taylor criterion, which is shown on the figure in the left. And in the principal space, in the space of principal stresses, it has this kind of shape, which if you cut through it, it looks like a triangle with curved corners. So this model is, we combine in our model a plasticity-based formulation for modeling concrete crushing. But for the modeling of concrete cracking, we use fracture mechanics-based model. And the model is a smeared crack model. That means we consider cracks to be smeared over the finite element size, which you can see on the second slide. And using this LT, which is the crack bend size or the size of the finite element where this cracking occurs, use this band to transform the fracturing strains into crack opening displacements. And then we can go into the softening law to properly consider the energy dissipated during the cracking process. Similar approach we use also in compressive behavior. There we have two stages of behavior. First, the material is hardening without any localization. And then we have softening where localization takes place. So again, a similar approach like in tension is used, but this time this LC can be referred to as some kind of crush band. Again, it is related to the finite element size. And this controls the energy dissipation during softening in compression. Of course, we have to validate our models, so we are validating them consistently or constantly through our work. But the best test is, of course, to participate in these kind of round-robin competitions where we don't know the result. Somebody is performing an experiment, sends us the properties, and we try to predict. Here you see some of our successes in these various competitions. Usually some positions in the leading places. And as you can see, it goes very long time back. Yeah? Already in 1982, that was my father at that time. He participated in a competition organized by Professor Collins. He tested these kind of shear panels, and the model, which is also still available in ATENA, at that time received the first place. Then maybe I would like to mention this competition at the bottom left. Gained first place, and this time it was ATENA an analysis, but performed by Dr. Il from Delft University. I always like to show it as an example that not only us in our office can obtain good and reliable results with ATENA. And the last very famous competition was this one in 2015, again by Professor Collins. He tested these kind of large shear panels, and our predictions were announced as the best predictions. So this is just to show that we provide very good predictions in the strength of concrete structures. Our latest, just to give you an idea what is our current state of ATENA, just now the official version has the number 5.7. And if I summarize the latest features and the newest development there, the main one is the durability models. So ATENA now has the possibility to consider deterioration. Main deterioration mechanism in reinforced concrete structures is, of course, reinforcement corrosion. So we have two models there for chloride ingress or carbonation. First, we, of course, model propagation of chlorides, and then the corrosion effect on the reinforcement. Another deterioration mechanism which is available in ATENA is also the alkali-silica reaction, ASR. Then there are new models for fiber reinforced concrete, simplified models based on the edit fracture energy approach. We have also improved the capabilities for modeling 1D beams and 2D shell elements. This allows to model large scale structures, where of course we cannot model whole building with solid elements, so it is advantageous to create a combined models, combining 1D beams and 2D shells with solid 3D elements. Another interesting feature is the ATENA cloud. So here we have a possibility now, or our users have the possibility to use ATENA in the cloud. So that means you don't have to install ATENA on your computer, but you can create an account on this cloud service, and this basically creates a computer with ATENA installed, and you can connect to it. And then you can pay as you go. There is some initial free period, and then later on you can purchase computing time as you need it. This is, let's say, good, especially for the evaluation of the software capabilities. So let me now move to this dynamic, which is the main topic of our webinar today. So in ATENA, we have two basic methods for dynamic analysis. Yes, if you see, this is the typical equation of equation of motion, where you have the mass matrix, accelerations, damping matrix, velocities, stiffness matrix, displacements, and some forces. In addition, ATENA has also this Hughes alpha method, which introduces alpha coefficient which introduces, let's say, additional numerical damping, which sometimes is advantageous for dynamic analysis. So that means in the end, we always have to solve a system of linear equations. But in this time, we have some kind of effective stiffness matrix and effective loading vector. From that, always an increment of displacement is calculated. Here you see how this effective stiffness matrix looks like. So you see it is composed of the mass matrix, damping matrix, and stiffness matrix. And here you see also these gamma beta, which are the Newmark parameters, and there is this additional alpha parameter for the Hughes method. So I don't want to go into details about dynamic integration of dynamic equation of motion. I want really to emphasize how these things are being used right in ATENA. So important, of course, is the damping. In ATENA, we have this Rayleigh proportional damping. That means the damping matrix is defined as a linear combination of the mass matrix and stiffness matrix with these alpha and beta coefficients. They can be provided in ATENA either directly, that you can specify the values of these parameters, or there is a possibility to use this model damping parameter, psi. That means you can imagine we are then solving this system of equations where we are trying to find parameters alpha d, beta d, omega I is the frequency, omega for the given eigenmode, and the psi I represents the damping of the given eigenmode. So in this way, you can, for instance, specify a damping parameter for the individual eigenmodes as they are calculated by ATENA. You can calculate them also in ATENA, the eigenmodes and eigenfrequencies. And then you can specify this damping parameter for the various eigenmodes. As you see, we need to solve for two parameters, yeah, alpha, beta. So ideal situation is that you define these psi for two eigenfrequencies. Of course, if you can do it, ATENA also allows you to define as many as you need. So you can even define more than two. But then, of course, you have a redundant system of equations. So it is solved by regression analysis. So these are the two methods how we can specify the proportional damping. Either directly by alpha beta, or you can specify total damping parameters. So as I told you, to control the dynamic analysis, we have these three parameters, gamma, beta, and alpha. Alpha is activated only if you select the Hughes method. And standard Newmark parameters, gamma, beta, always, of course, has to be defined always. And these are the typical values. So this, if we select gamma equal to 1/2, beta equal to 1/6, this is like defining linear accelerations in a step. Constant acceleration corresponds to the gamma equal to 1/2 and beta equal to 1/4. This is, let's say, the most optimal parameter definition. And in order to have a conditionally stable solution, you need to satisfy this condition for gamma beta. These are, let's say, the known conditions. But in addition, if we are considering Hughes method, then the limiting value for alpha is 1/3, minus 1/3 to 0. And then we have to correspondingly adjust the gamma beta parameters. So this, in addition, I should mention that there is also a Wilson method, but I don't want to spend more time on this today. We generally recommend the Newmark method. And in case you are experiencing some convergence problems, we recommend this Hughes alpha. Here are just some small examples to show the effect of these methods. So if we, for instance, consider a pre-vibration of a mass on a spring, and if you compare the results, you see that this Newmark method has a much better matching with the analytical solution. Use method already starts to show some divergence from the solution as we go through. Similar situation is with the sinus load without damping, sinus load with damping. This is just to demonstrate what can be the effects of these various methods. So now let's go in more detail how this is analyzed in ATENA. So I'll be concentrating on ATENA science using the Git preprocessor, because actually ATENA science is the only version which supports dynamic analysis. So for those of you who are familiar with ATENA know that we have also ATENA engineering, 2D and 3D, which only supports static analysis. So if you want to use dynamic analysis, you should use ATENA science, and then you have to use a GID program as a preprocessor. And GID, you always have to activate the right problem type. This is from the menu data, problem type ATENA, and there you see the 4 problem types which are supported right now, which is the creep for modeling long-term effects, of course static analysis. Then we have a transport module, which can be used for modeling heat analysis and also moisture transport. But in this case, we should select dynamic. If you do that, you often get this kind of message where, especially when you already are using, for instance, a model from static analysis, it will ask you whether you want to reset to the new problem type or just transform it. Generally, I recommend to use transform, because it will try to transform any boundary conditions and material properties which exist already in your model into the new problem type. In some cases, it is, of course, possible to use it, mainly, for instance, from transport analysis, because in transport analysis, the material models are totally different. But when you are switching from static analysis, for instance, to dynamic, very often you can use many of the existing boundary conditions and material definitions also in the dynamic analysis. So I recommend to use this option transform, because if you use this reset, it will just keep the geometry, and all the boundary conditions and material properties will be deleted, and you will have to define them again. So I'm now checking whether there are some questions. So please use this chat window. Don't see this Q&A section. See it now. So probably you can also use this Q&A section. To tell the truth, this is the first time I noticed this option in WebEx interface. So I'm not exactly sure how it works. So preferably ask your questions into the chat window. All right, so this is the basic idea how to select the problem type for dynamic analysis. And now let's talk about how to define these key parameters. So if you remember, in GID, we can click this key, which opens this problem data window where we can define various global settings. I don't want to talk about these other tabs here. We should concentrate now on this tab, which will this tab called time and dynamic. This dialog appears if you select or if you activate the dynamic problem type. And there you can define, there you should define the range of your analysis. So that means when you will be starting, what will be the final time. And then you select this analysis method, which can be either Newmark. In this case, use alpha method is selected. And in this case, you have to define the alpha parameter and these beta and gamma parameters. You may notice here that now these beta gamma parameters are selected according to these previous conditions that I have defined here. So you should satisfy these conditions in order to have a unconditionally stable algorithm. An important part is this damping definition. So either I told you there's a possibility to define the two parameters directly, or what I'm showing here in this dialog is now the possibility that I can define damping model damping parameter for different eigenfrequencies. Yeah? So in this case, I can define a set of eigenfrequencies in terms of omega and their damping parameter. This is like a relative value. So if it is 1, you can think about it as a 1% damping of this. And then the program by regression analysis determines optimal value of alpha d, beta d, satisfying these 6 equations. Now about the material parameters. In terms of material parameters in ATENA, let's have a look how it affects. Let's have a look, for instance, at the concrete material parameter, which, as I said, is the main material we are working with in ATENA. So in ATENA, you can generate the material parameters properties based on the strength classes or the cylindrical strength, compressive strength of the material. It then generates some basic parameters like modulus, Poisson ratio, tensile strength, compressive strength, tensile properties. Important parameter there is fracture energy, fixed crack, whether we have a rotated or fixed crack. Crack spacing is an important parameter where we have large finite elements. So in this case, we can expect that there will be more cracks inside one element. So it is important to find this crack spacing. And most important is, let's say, this last or this miscellaneous tab in terms of dynamic analysis, because there we have the density of the material, which is important for the mass matrix. And if need be, we can also activate a particular damping coefficients for this material. Of course, in many cases, you don't want to do that, but if you want, you can activate particular damping here and define the damping coefficients for this particular material. If you do that, then this will override the previous definition of the damping, as I mentioned, the problem data dialog. So that original definition, that global definition will be used for the whole structure, with the exception of the materials where particular damping is activated. Important part for dynamic analysis. Of course, I'm apologizing, but I kind of expect that some people understand ATENA and know how to use ATENA. So I really concentrate only on the aspects which are different for dynamic analysis. So in the interval data, we have to define, they're defining the history of loading. Dynamic analysis, typically, in this case, I want to show how this is done for a seismic assessment by accelerogram. And in this case, we have to come up with some loading scenario. So typical loading scenario is that we first apply boundary conditions and self-weight of our structure. Then in the next interval, we add maybe some additional dead load for the structure. Then we apply live loads for the structure. we always have to define appropriate. This, of course, should be with some longer time because we want to be sure that we don't have any effects, dynamic effects from this loading. So as you can see here, we are applying it in several seconds, all these loads. And then most important is this fourth interval, which activates the accelerogram. Spend more time on this one. So we apply an accelerogram to our building, which you see kind of in the back. This is also an example I want to show you later on with some results on this example. So this is a 18-story building, which is subjected to accelerogram. And here we define basically the time of the accelerogram, which is from 2 seconds to 12 seconds. And we, in this ground accelerogram option, we can define an input file containing this accelerogram. In addition, I want to mention one option for the users who are using ATENA. Sometimes they don't know about this option, but you see there is this, when you define interval data, there is this additional load cases tab, which can be used to define, to reuse some of the load cases or some of the boundary conditions from previous interval. So for instance, normally every time you create an interval in GID, you have to repeat the conditions which are fixed, let's say, yes. For instance, typical condition is the support. Support should be in all intervals. So that means you have to define it or copy it from one interval to another. This is, of course, possible to do, but sometimes awkward, because if you have a lot of intervals and then you suddenly find out after defining, for instance, 20 intervals that you made a mistake in the supports, it is very tedious to go and make the correction in all intervals. So what is better to use these additional load cases and reuse the conditions from the first interval. For instance, you know, in my case here, in the first interval, I defined boundary conditions and maybe also some fixed contact conditions. And now in all the other intervals, I can just say, okay, use the data from interval 1 with maybe multiplier 0, because I don't want to multiply them by anything. They are just supports. And I can then reuse them. So this is something I want to mention. Some users of ATENA may not be familiar with this, because this is a relatively new feature there, and it simplifies greatly the definition of. Now let's go back to this accelerogram. So this accelerogram is actually a very simple file defining the time and the acceleration. 2 columns, basically. And then we just say, okay, the accelerogram should be applied in X direction or Y direction or any direction. So, okay, so these are basically the main steps we need to, which are different in the dynamic analysis from a static analysis. So we have to define the parameters for the dynamic analysis. We have to select the appropriate method. Then we need to ensure our materials are properly defined and that we have defined the mass there. Here maybe I should mention that this mass definition of the materials, if I go back to this dialog here, mass definition exists also in static analysis in ATENA, also in creep analysis. And there it is actually not used for anything, yes, except for the eigenvalue analysis. Because even in static analysis, ATENA allows you to perform eigenvalue analysis. I just want to emphasize this because some people think that if you define mass density, that it is used as a self-weight. It's not like that. The self-weight must be defined as loads. So this raw density is really used only for mass calculation, which is used in eigenvalue analysis or in dynamic analysis. So let me now show one example, kind of a validation example. So it is this stop here, post this video. It comes from this CAMUS experiment, which has been performed in France, where they tested this kind of model, which represents a 5-story building. It was scaled down, and this shows the model, yes, because you see it's kind of symmetric. So we modeled only half of it, with main emphasis on modeling the wall. The slabs are there mainly to properly consider the masses. You see the reinforcement. So there were two ways of reinforcement modeling. As you know, in ATENA, we can either have this discrete reinforcement, where each bar is modeled individually, or we can also introduce the reinforcement as a composite material. So that means we add it into the material. This is what we call the smeared reinforcement model. So for the reinforcement in horizontal direction in the middle of the wall, this was modeled with this smeared option. But these important vertical bars, which contribute significantly and their proper location should be taken into account, they are modeled individually. This shows the result. You should hear. Oops, I'm sorry. This is the video. Let's continue. Video. That was a parametric analysis that I showed you. I want to come to that later on. So this is the model. Talk about that, and here you see in the dynamic analysis. So you start to see what this graph is monitoring. On the horizontal axis is of course time, and on the vertical axis is the displacement at the 5th floor. So you can see how the cracks are opening, closing. This gray area indicates basically crashing of concrete, which actually very nice. There will be also a picture, a photo of that, very nicely corresponds to what happened in the experiment. Yes, there was this crashing area exactly at this location. And this was the crack pattern in the experiment. This shows the comparison of the, I will come to that. So if you see, this is, let's say, the comparison with the best fit. Of course, in this case, we performed the advantage that we are performing the analysis, knowing the results. Yeah. So of course, this is a very nice matching, but of course, you have to take into account this was done afterwards. And that's what I want to talk about now, is to give you some idea of the sensitivity of our results to various parameters. So the red line and the black line is the analysis with ATENA using the Newmark method with the beta gamma parameters corresponding to the constant acceleration approach. And if you, it is interesting to see what happens if we use this use alpha method. Yes, if we activate this use alpha method, which you can think about is adding some additional numerical damping. So you can see that this method works quite well actually in these first cycles, but then we start to have some deviation from the correct solution. On the other hand, you can still see that let's say the peaks and the amplitudes are more or less correct. Let's look at other result if we consider different damping ratios. So again, red one is experiment, black one is the first analysis, the optimal one. And then what happens if we use the Xi 5%? That means if we consider 5% modal damping. This is the blue line. So you definitely see again, first peaks are pretty good. And then we start to see that response is is a little bit damped. It's too much damping is considered there. It is also interesting to see if we totally turn off the damping. So you see, of course, right from the beginning that we have a little bit higher peaks, but still the results are, let's say, not so bad. So this means that many of the damping comes from the nonlinear effects, from the cracking and dissipation of energy in the cracking process, which actually the program considers without any damping necessary, without any additional damping. Let's look what happens if we use different time steps. So the initial analysis was done with a very fine time step, very small time step, 2 thousandths of a second. But if you look at the results with, that's the blue one with the 200ths of a second, you see a very small difference. This is almost identical to the black one. But of course, as we increase the step size to already 500ths of a second, that's the green line, you can see that the results is not so accurate anymore. But still, let's say you can say the overall trend is still captured. Okay, let me show another analysis. This is, let's say, a little bit bigger model. I just want to show this to demonstrate that this can be done. This analysis, for your information, so it's the same building I showed a little bit at the beginning. It is this 18-story building. Using actually the same accelerogram as for the CAMUS analysis. And so you can see it, how we can simulate the cracking, how the cracks is opening, closing. With this model, of course, we used this. Back to the model here. Stop it. We talk a little bit more about this model. This model is using quadratic elements, or relatively, so we can use a coarse mesh, and it is using these shell elements of ATENA. That later on show you how this is being done. And the reinforcement is, of course, in this case, we do not model each individual bar. This would be really too complex model. So the reinforcement is considered as a special layers of these shell elements. Okay, so let me stop with this presentation. I will go and check various questions here. Okay, so Pavel is asking how to determine particular damping coefficients for concrete. Well, this is, of course, a big and difficult issue. Typically, I think have to make some engineering judgment here. Typically, I think approach is that we consider something between 1% damping to 5% damping. This is my understanding. This is the typical situation. So Of course, as I told you in this analysis, that's why I wanted to show that the result is not so critical. Yes, if we, for instance, look at these results. So if you look, I considered here really the extreme situation that I don't consider any damping, and I consider damping 5%. So especially if you consider the result between 2% damping and 5% damping, which is the blue line and the black line, the difference is not so big. Good thing is that ATENA, of course, considers additional damping, which happens due to cracking or reinforcement yielding, or in ATENA, we also have a bond model, so we can consider the slip of reinforcement inside the concrete. So all these things represent damping also. These kind of dampings are considered, let's say, automatically based on the real material behavior. So the only damping that actually needs to be considered is the viscous damping. That means the damping of the material in its, let's say, elastic regime, which is typically not very big. So this is, of course, a problem. Yes, the damping is a research area of its own. Asdam is asking whether we could explain a bit more how the damping regression differs to the damping coefficients, which one is normally used in the modeling. I'm not sure I understand the question. We are using the Rayleigh damping, maybe show it, GID interface to make this clear. Under this problem data, you define either damping by coefficients, that you define directly the coefficients for the mass matrix or for the stiffness matrix. But these, in my opinion, are a little bit difficult to identify. So much better is to define these psi parameters for the various modes, eigenmodes, which I think are, let's say, easier to estimate. So because we need to define these two parameters. So ideal is to define this psi for two eigenfrequencies. Typically, for instance, the first two. We will define the omega for the first frequencies, for the first two frequencies, and the corresponding psis. They can be, of course, different, but it's 2%. The second question from Asdam was, in the dynamic modeling, what boundary conditions are activated to define the acceleration load, which will be later on taken into account in the interval data? Well, yes, the acceleration, as you can imagine, typically is applied here at the bottom of our structure. Yes. Structure. So in ATENA, you have two ways how to do that. Either you can define or prescribe an acceleration condition here at the bottom, but much better way is, rather than this prescribing acceleration condition here, is to fix your structure here and apply the acceleration as forces on the top. That means from the accelerogram, you always take the acceleration, the accelerogram times given mass at each point, and you apply that, in this case, the accelerogram as forces. Of course, you can do it also use this first method, as I told you, that you prescribe acceleration at the bottom. But the problem with this approach is that as the acceleration is applied, I'm sorry, the structure will start moving. So it will be moving through your screen. Sometimes this movement may be bigger than actually the relative displacements of your structure. So it is then difficult to see the shape, the deformed shape. So much better way is to use this other method. And that's the method I was showing. If you, in this interval data, you define this ground accelerogram, this is this method that you are applying acceleration to the whole mass by multiplying the masses by the given acceleration, and you have to fix it at the bottom. The other method is to use the condition from GID. In these conditions, if you see, you can, one of the conditions is acceleration, for instance. So if you use that condition, you can describe it as a value. And in addition, you have a possibility to define a function. So in this case, you can also provide some time history for these accelerations. Let me go through the other questions. Maybe they have been actually answered already by my colleagues. Can you share the presented models? Is asking Pavel, or include them into standard package in ATENA installation? Yes, this will be the case. Yes, in the next version, which we are now preparing, it will be the version 5.9, which we expect beta version to be released next month, and then the final version sometimes during the summer. This example will be there. But if you are interested to receiving the data, please send us an email and we will also send you. Abhijit Kulkarni, I'm sorry, I may not pronounce it correctly, is asking, what was the time required for this analysis? Yes, that's a good question. I assume you mean this big one. Yes, and you can see it here if I start this video. Pause it here. Yes, the analysis time was 20 hours of this 18-story building on Intel Xeon with 4 CPUs. As you know, in ATENA, we can use of the fact that new computers nowadays, they have several CPUs. In this case, it was 4 CPUs. Each CPU typically has 2 cores. So we have actually 8 CPUs to run in parallel. So that's what was used. It is a Xeon computer, but let's say already about 5 years old or 3 years old. So it's nothing really special. So you can run this analysis overnight, basically. Well, overnight is 1 day. But the other analysis, if you were asking about this CAMUS experiment, this one takes about, was depending on the time integration, but with this very small integration time, which was original, which was about 2 thousandths of a second. So it took about 1 hour. So let's go to another question. Farhat Dashati is asking, was the slab modeled as elastic elements? Yes, in this case, for instance, slabs were not really interesting, so we modeled them as elastic elements, elastic material. Also in this 18-story building, the slab was elastic, because it was, we were not so interested in that. But there is no problem really to activate also nonlinear elements. Of course, this may analysis more demanding. Problems then will be that the slabs may start failing, so you may have problems reaching the convergence and so on. Pavel Ostrovsky is asking how to consider concrete properties variation due to high strain velocity. yes, this is not available in ATENA right now. I think for this seismic analysis, the effect of high strain velocity is not important. But if you consider some blast loading, it may indeed be very important. On the other hand, this blast loading is very fast effect. So in the end, you can maybe, if you know how to, you can already, for such an analysis, consider that in the definition of material properties. So you can increase them as you think. On the other hand, I must say it is a still open question. Yes, this dependence on high strain. It is a question whether it is not really I think there is still some discussions whether something like this exists. Maybe it is just really an effect of inertia forces on a micro scale. Okay, another question by Mr. Effendi. In ATENA, can we to modeling some structural elements that have been damaged, for example, model a crack in building after an earthquake? There are additional parameters for these elements. Well, I am not sure where this equation or where this question leads, but of course the cracking is automatically calculated, or the damages from the earthquake are automatically calculated by ATENA. So for instance, you can make a seismic analysis of ATENA. This calculates the damages, and then you can load such a structure after that to evaluate its strength based on the damages. Otherwise, the damages, of course, can be introduced, for instance, by reducing the material parameters like tensile strength in the damaged areas. That's, let's say, the best way how to do that. Or we can also introduce some interfaces to simulate some pre-existing cracks. This is the other question. Perhaps it is possible to apply the ground motion components by different load cases. Sure how this means, but in case, but yes, you can, this load history, you can define any history you want. You can define various load cases and then you combine them together for different ground motions. Yes, this can be done. In addition, sometimes we are encountering some situations. What I want to say is that in ATENA, if I show you, switch out of the presentation mode, show you some existing analysis, which I have just here opened. In ATENA, always you have an access to the input file. So sometimes some things are maybe not fully supported in the Git interface, and more commands, much more commands exist actually in the side of ATENA. Very often you can directly modify this input file, and you can actually make a lot of things in addition, which may not be even supported by the user interface. Of course, we are gradually introducing all of these features in the user interface, but still there are some cases where they are not supported in the user interface, but still supported inside the program. And the only way how you can access it is by modifying the input file. Okay, another question is by Mr. Kulkarni. Hello, are there any example of built-in SFRC material input? Yes, there are many examples, and we are adding more, especially now in the new version, which I already mentioned, 5.9. We have substantially extended this example section and also the example how to easily access it. So there will be some kind of a front end which allows you to manage this input file or this access to ATENA easily. So there was another question Is it possible to run an unreinforced masonry structure? Yes, yes, sure. But you have to adjust the material properties to that. How was the seismic mass included in the analysis? Seismic mass included in, that means D plus 0.3 L. Yes, we already answered the question from the applied dead load and live loads in the previous interval. Exactly. So you have to, in the previous intervals where I was applying the dead load and live load, I would of course apply the live load only up to the level that we need to consider in the seismic analysis. Christoph Gzip is asking, is it possible to get results, for example, displacement in each node, not only in monitoring points? Of course, of course. When you go to post-processing in ATENA, you can, of course, display the standard results like in any other program. So you can, for instance, contour plots of displacements, action, and of course, it is also possible to print them out into the text file or to make a selection of given nodes and then create a printed output for displacement at these nodes. The monitoring points is a useful thing, especially if you want to monitor something during the analysis. But sometimes you forget to add some monitoring points, or later on in the post-processing, you realize that you need result or evolution of displacement in time at some other point. So you can create a monitoring point even when the analysis is completed and ask the program to extract the data for this monitoring point from all steps. Last question here from Ingrid Rozio. Is it possible to do retrofit, e.g. SFRC for this type of analysis, as in static analysis? Yes, you can do that, because like in static analysis, you can have very complicated loading. So after this interval with the seismic load, you can add another interval where you can modify, add some elements, and then make some additional loading to see the effect of these other structural elements which were added to the structure, which may simulate the effect of the strengthening. Of course, what is not currently available, and we are working on that also, is that to take the results from the dynamic analysis and continue in a static analysis. So once you are in a dynamic analysis, you have to stay in the dynamic analysis, but of course you can introduce a slow loading so that simulate the effect of the retrofitting. All right, I think we are running out of time. So I will conclude my presentation today. Thank you very much. And yes, we will make this presentation available also as a video, which will be placed on our YouTube channel, also provided to the registered participants. So again, thank you for your attention, and hope you will stay interested in ATENA, and hope to see you some next webinar, or hopefully maybe personally at some conference. And I want to mention also, please, if you have any questions or problems, do not hesitate to contact us by email, chervenka@chervenka.cz. Thank you.
ATENA program produced by Chervenka company. You can find us via the website and download the program from it, or on YouTube by name Chervenka Consulting, or in Facebook by name ATENA. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.